Hi, welcome to Mat210 Elements of Calculus. So in this section, 4.2, we're going to talk about something called area under the curve. We're going to use integration and some other techniques to help us find the area under a curve. And this was first one of the mathematicians to come up with an idea how to find the area under a curve was a gentleman called Riemann, Reiman. And he did a series of sums. And from Riemann's sums, we're going to learn a little bit about how to do various things. Okay, we're going to use Riemann's sums to help us find summation under a curve. And then we're going to find how to write summations using summation notation. And then we're going to learn about a little bit about how integrals will help us find this area. So what Riemann did is he took a curve. Let's start out with this one. He took this curve and he was trying to figure out maybe the area underneath it. So he said, well, let's divide this up into a series of rectangles. And then we'll find the area of each one of those rectangles and we'll be able to find the sum. Now, what I'm going to do is I'm going to start at the left side right here, where it hits the axis or where it hits a thing. And I divided this up into 4 units along the bottom. Sometimes this bottom is called delta x, delta meaning the distance of x. So this could be called delta x on each one of these. And of course, this is our y value. Sometimes we call it delta y, or we could just call it y or whatever. This is basically your height. Okay, this is the height coming up. So I thought it was convenient to take my curve and divide it up so there was 4 units each time going across the bottom. And then what I did is I started from the left side here. Now notice we do have a gap here. Okay, but this area inside here is 16. Then I did the next one. I came up here with this, I think went 7 by 4. So that was 28, right? And then I started at this point, and notice it goes beyond the curve. But that's okay because that area maybe fills up some of this missing area. So we can kind of think, okay, that's going to go in here. And then I did the same thing here. I started on the left point, and it kind of went beyond the curve. But that's okay. That gave me an area of 5 by 20. This was 5 high. This was 7, and I think this was 4. So I was able to calculate the area of each one of these rectangles. And this gives me an approximate, and then I added them up, 16, 28, 28, 20, and that gave me an approximate area of 92 under this curve. And some of these areas are going to fill in here where I didn't calculate that space and I didn't calculate this space. Well, then I said, okay, what if I did it from the right side instead of the left side? So the points now are on the right-hand side, right side, right side, right side, right side. So now my triangle looks like this. My rectangle. This was 7 by 4. This was 7 by 4 also. I used this point right here going across. And I used this point and kind of came across here. So it was this rectangle right here, which was 20. And then this one right here only went up, let's say 1, 2, 3 units. So that was 4 by 12 is 6. So this went up 4, 5, 7, and 7. And I figured, well, this extra area fills in here, mostly there. Might be a little bit short, we'll see, because it has to fill in here, here, and here. So when I added all these numbers up, I came up to 88. So I figured the average between these two was about 90. So this one might be a little bit high. This one might be a little bit low in our estimates. So I figured it would be about 90 is the area under here, 90 units, whatever, and so on. Okay, well, then I said, well, what if I took these units and I split them up using the left hand. This is, it says right, but it should be left. This is left. I don't know, I can't tell my left from my right. Using the left again, let's cross that off. This was left. And I did the same thing, only this time I split them in half. So I only went 2 units. Delta X, instead of being 4, delta X is now 2 units, right? And I went up 4 units by 2 and 10 units. And this would be 5 by 2. This would be 7 by 2, 8 by 2, goes a little bit over. 7 by 2, you see there's a little gap here, but that can kind of fill in. Here's another one, 12 by 2, 10 by 2, and 3 by 2. This was 5 by 2. And I multiplied them all out. And then I added up all these areas and it came up to 90. So a little bit more accurate maybe by splitting them up. And we could even do it again. We could split them up at 1 unit and up so many, So I just did it by 2s. And then I did it again from the right-hand side, which is the left-hand side, but it should really say right. And for the right-hand side, and did the same thing, 5 by 2, and 6 by 2, and 8 by 2, and 7 by 2, and 6 by 2, 5 by 2. What was this one? 4 by 2, and 3 by 2. And I added them all up and I came up with 88. So maybe if we put these together, 90 and 88, maybe that would be a closer approximation. I don't know. That would be 178, divided by 2 should come out to be 89. So maybe 89 is a little closer number. I'm not sure, but just taking the average of these two. And sometimes we do them various ways. But this is what we mean by Riemann sums. We just add up the sums of all these little rectangles. Now, you can get more accuracy maybe if you went to the middle point of each one. You could draw a rectangle that goes to the middle, to the middle, to the middle. And sometimes that's a little bit more accurate. And then another way we could do it is we could do with trapezoids. Of course, that takes more math, but we could have designed this as a trapezoid. And sometimes we call these finding the areas of the various trapezoids. And sometimes in Calc 1, they spend a lot of time on Riemann sums, finding it by left hand, right hand, middle, trapezoidal, and so on, and we come up with them. So we know there must be an easier way than doing all this. And this is where antiderivatives is going to come in. But this is kind of our basis for it. So this leads us to another type of thing called summation notation. Because as you can see on these problems, we were adding up all the sums of each one of these areas. And that leads us to a summation type thing. So in summation, what we do is we develop a formula. And here we might have developed a formula using the curve, but I don't really have an equation for this curve. It was just made up curve. So I kind of just made up a curve and but it's the same curve each time, or relatively close to the same curve I was trying to draw each time. So on summation notation, and you can find this kind of in your book on page 403 that kind of leads into it. But let me show you how it kind of works. Let's say, let's look at example 8, where we actually have what? We use a symbol called sigma. Sigma means the sum of, okay? And down here on the bottom, we use some variable. We usually use letters like I, J, K. We use those kind of that area of the alphabet that we don't use too much. We could use an N if we wanted to, but we usually use the letters I, J, K. And this represents our beginning point, our beginning number. And then the number on top represents, on this particular one, it was a 4, represents our last number, how far we want to go up to. So we want to start with a 1 and a 4 up to 4, and we're going to substitute in consecutively. Now we need some kind of function in here. So they gave us a function where this is 3 to the I power. Okay, this is not meaning the letter I. It means I is going to start out with 1. It's not the square root of -1. That's not what they're saying. They're saying this is a variable that's going to be changed all the time. So sometimes, in math, we can get a little confusing. Sometimes, like in trig, when we use a -1 there, we actually mean the inverse and not 1 over the sign. And in this notation, we're saying 3 raised not to the I power, but actually to these numbers that we're going to substitute in. So what we're going to do is we're going to start by substituting in a 1. This would be 3 to the 1. And then we're going to go consecutively. Now we're going to put in a 2, and then a 3, and then and we're going to, finally, when we get up to 4, we're going to stop. So this number doesn't have to start with a 1. It could start with a 0 or a -1 or a -2. This is just our starting number, and this is our ending number. We're going to go up to that. So this doesn't always have to be a 1. It could be a 0. It could be -1. It could be -5, whatever. But each time we're going to do it consecutively. So this would be 3. 3 plus 2 is 9. 3 plus 3 is 3 to the third is 27. And 3 to the fourth is 81. And then what we're going to do is add all these up. This looks like it would be 90 plus 30 is 120. And you could do that on a calculator. So the sum of these would be 120. I'm just double checking with the book. Yeah. So let's try a couple more of these, see if we can do them. Let me give you a little bit more summation notation. And it's really a pretty easy notation. Let's draw a sigma here. And let's use a J so we aren't so confused. And let's let J equal 0. And this is going to be 5. And our formula is going to be 2I. Okay, pretty cool. So we're going to start with 2 times 0 plus 2 times 1. Let's put them in parentheses. Plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. And then we stop at 5 because 5 is our last number. So 0 is our beginning number, 1, 2, 3, 4, 5. And then we're going to calculate. So 2 times 0 is 0, plus 2, plus 4, plus 6. Looks like we're getting all the even numbers, huh? Plus 10. And then we're going to add those up. Let's see, 4 and 6 is 10, 2 and 8 is 10, and 10 makes 30. So these would add up to 30. And you could use a calculator to add them up or whatever. Okay, let's use another one here. Let's go with I again, and I is 0. And we're going to go up to 5. And we're going to use a -2I, like that. So this is going to be -2 to the 0 plus -2 to the 1 plus -2 to the 2 plus -2 to the 3 plus -2 to the 4 plus -2 to the 5th. So you could say, if this went up to 25 or something, maybe there's a quicker way on a calculator. So what is -2 to the 0 power? What is anything to the 0 power? 1. What's -2 to the 1 power? It's itself, -2. Plus -2 squared, -2 times -2, +4. -2 to the third, negative 2, negative 2, negative 2, negative 8, plus negative 2, negative 2, negative 2, negative 2, positive 16, and finally negative 2, negative 2, negative 2, negative 2, negative 2, negative 32. Okay, so what I did on this one is I added up all my negatives. I got negative 42, save a little bit of time. And then I added up all my positives and I got 21. So my answer is a negative 21. Okay, so that's all there really is to it. And we do want to find the sum of these. That's what we're asking for. This means sum of this thing. And we can also use it if we got something really weird, like suppose we had something like this. We use I again. I begins at 1, it ends at 4. We've got a function of x sub I. So this is saying we got a function, and this is our problem here. And so this would be x to the 1, sub 1, x sub 2, x sub 3, x sub 4. And we can't really do anything to that. We can't add them because we don't know the values. And that's kind of what we were doing here. We had x sub 1, x sub 2, x sub 3, x sub 4, but each one was a little different. So we can't really have a universal pattern. X sub 1 was just simply on this, if we use this top problem, it was 16 plus 28 plus 28 plus 20. We're showing that we're doing this, and we might have even done this as x sub 1 was the area underneath here. This equals the area, x of I should say, was the area. So we add up all those areas and we came up with 92. So we can use summation theory to kind of help us on this one. Well, over the course of investigation, and maybe this is one of the things that Newton came up with, or Leibniz, and they were messing around with this kind of idea, saying, God, there's got to be an easier way to find these areas. I mean, this is pretty good, but the more boxes you draw, and if you draw 100 boxes under here, you're going to get more accuracy than if you draw 4, or if you draw 100 trapezoids, you're going to get a real accurate answer. But man, that's going to take a lot of time. So they came up with an idea, the concept of using an integral. Now, we've been using integrals in the last section, but what they came up with was this idea, a definite integral. And let me show you how a definite integral works. I don't know if you have too many examples in your book. They didn't, this is just kind of a cursory thing. So I'm going to show you some problems on page 409. On page 409, you have some problems 11 to 38. And I'm going to show you what they're talking about. Here's the integral, 2 to 0. And here's the problem, 2 dx. So what they're saying is, if we had this equation 2, we had a function 2, 1, 2. And basically this is what the y value is. It's shooting across here. It's just going to be a straight line. And we wanted to go from 0 to 2. What would the area be underneath here? What could we assume the area under here would be? Well, this one being a very easy problem, we could take a look. We could just actually count. Let's divide this up into boxes. This unit right here is 1. So 1 times 1, this is 1. This is 1. This is 1. This is 1. It looks like it would add up to 4, huh? The area under this curve, which isn't much of a curve, it's just a straight line. And this continues. We're just using an interval from here to here. And we're seeing, okay, what's the area inside this box, inside here? So this would be, we could also say this was 2 units long and 2 units high. 2 by 2, 4. Okay. So the way we would do it with integration is we would write the integral of 2, which is what? 2x to the 1 over 1 from, and we want to show, and different people have different ways of showing this. I write it like this. We always start with the small number from 0 to 2. From 0 to 2. And then what we do is, want to maybe simplify this. We don't want all those ones. So this is basically just, I write it down here, 2x. But notice we didn't write the c because this is a definite integral. It's going to go from 0 to 2. So we don't write the c down on this. We just write 2x, not plus c, not plus some constant. And what we're going to do is we're going to substitute in the top number, which is 2 times 2 for x, minus, we're going to subtract the bottom number and we're going to substitute it in, 2 times 0. And you see, this is going to give me 4 minus 0, which is 4. So the exact, and this will give us the exact answer to this problem. So this one being fairly easy, but to get you an idea. So this is called a definite integral. It goes from 0 to 2 dx. The integration is 2x, basically just 2x, from a value of 0 to 2. The top number we put in first, then we subtract, and then we put the 0 in, and then we calculate the difference between these two. All right, so let's try one that's a little bit harder. That one was pretty easy, and this one won't be too much harder. Okay, we have this integral, and this one goes from 2 to 6. And the integral is 3 dx. Okay, so this is going to be, I don't know where this, excuse me for just a second. I don't know what's going on here. Anyhow, don't worry about it. So this is going to be, what is the integration of this? It's going to be 3x power is 1 over 1. So I'm just going to write 3x from 2 to 6, 2 to 6. So first I'm going to put in a 6 minus, and then I'm going to put in a 2. Then I'm going to calculate 18 minus 6, 12. So the answer to the definite integral of 3 dx is from 2 to 6 is 12. If I didn't, hopefully I didn't make any mistakes. So you can see it's not too hard. Let me try one just a little bit harder, and then you get the idea. Let's try this one. This is probably the hardest one. Try this one. This is number 39 if you have a book, but this is on page 409. Just like the cleaner, we're going to clean up on these problems. And this is, here we got a problem that's a little bit more interesting. 10 minus 2x dx. So let's find the integration of this. Okay, so the integral of this would be 10x minus 2x squared over 2, right? From 2 to 4. It should always start with the bottom up, 2 to 4. I guess if we said 4 to 2, it wouldn't be so bad, but we usually start with a small number. Okay, and we could simplify this a little bit, huh? So this is nothing more than, I put it over here, 10x, which was over 1, minus x squared, 2 to 4. So we're going to put a 4 in here first. 10 times 4 minus 4 squared minus, and then we're going to put a 2 in here. 10, let's put another parentheses, times 2 minus 2 squared. Okay, so first we put in a 4, then we put in a 2. So this looks like this would be 40 minus 16, which is 24, minus, this would be minus this whole thing, 20 minus 4, which is 16. So this would be 24 minus 16 gives me 8. So on your quiz, you're going to have some, let's go back here. We're going to have some evaluations of these summations. And then we're going to have some of these things, not too much on Riemann sums. I have a little extra credit where you can do it by Riemann sums and try to figure the area under it, approximate area using Riemann sums. But basically just kind of learning how to do summations, because we do summations a little bit later, more advanced in calculus, and then something doing these curves, okay? Just simple curves, and then we'll work on some more complicated ones. So I hope you enjoyed this.